put the yellow over? Not too bad. You finally made it in last night. What time did you get in? Like 1 o'clock in the morning? Oh, I thought you weren't getting in until 11 o'clock or something.
We were supposed to.
Oh, great. No, I'm his lackey.
Yeah, I don't think that's a Deirdre. That's River. Yeah.
Okay, I'm not really.
Carol may have found that. Did you find the website?
No, maybe found the link. Yeah.
Yeah.
But it's just saying that it's
Shall I close those?
I don't know.
Do you want me to try?
Yeah, you can try it.
Turn the lights down?
No, the lights aren't on. Oh, I think they're on. But
is everything okay?
yeah, we're just gonna.
Did you succeed in connecting?
Yes, it all worked, no problem.
Perfect.
So we're just gonna try and close the blinds because
Yep.
the image
There's
is
a
a
glare.
little bit shot out, so you can't really
Yeah.
see the screen super well.
Oh yes. You can see it all.
Yeah. So, unfortunately, hopefully there's not as much sunlight. But, that's okay. Big rush of people at 1 o'clock.
I guess. Expecting more people from this.
I think so, yeah.
Almost have no. That's what we call have. You all earned your way in here. And it's so interesting, so all these studies, which entitled kids don't sort of get any lower income students and students. Yeah. Yeah, they make it But I mean, if you come from if your family are millionaires and billionaires, you don't really need an added boost.
Better. No, I don't think it's going to get much better.
And they're also some of the same people who are.
Yeah, well, it's something in the cable.
And you don't have any other cables?
I did my adapters because she had a presentation and I haven't gotten them back yet.
Absolutely. And it's not multiple choice. You got to write on the explanation. done?
Yeah.
Let me ask Deirdre. I'll go ask her.
I'm going to have to stand on this.
Yeah.
I'll dust it off. I'm not. The webcast's not on yet.
Oh, probably not Amy's lane.
Yeah.
Yeah, I'll eat first. You have to sit in the front row. I'll tell people to the front.
Pretty good. Finish Grasselli. Yeah.
Awesome.
Pretty crunch time.
He's coming to California to look for a job.
No, he's not.
As soon as you become an independent
It's at a time now. Come on out, I'll tell you.
Yeah. Well,
We
you're
have the 6th largest economy in the world.
yeah. I mean, your governor was talking about that.
Yeah. Past France.
Wow. So, compared to the other states, like, you number one in the US? Yeah. Yeah, with all the,
Silicon Valley.
yeah, and the Napa Valley and everything else. But you know, you always ask the question. Why is it anything even miracle? But there's still the
Probably I wouldn't have been on one. So I'm not. That's kind of like the biggest thing. I don't know off the top of my head. Yeah. Oh yeah. It's much more similar to a Hamilton. I'm not really a big city person. I just don't really enjoy lots of people. Yeah, exactly. Yeah, pretty much. Yeah. Yeah. So, I'm hopeful that things will be pretty fine, and that ideally if I'm working in the government, they will probably be paid for like that. That's the way. Yeah, there's stuff that I'm kind of reflecting on. A lot of jobs require pretty significant security clearance in order to
That's why. We just call them games.
Oh, no, it's okay. We got it back. So that's
I need to tell them that we have to shut down. I know.
it's a little bit worse than it was before. Yeah, I just talked to her.
So when everybody sees it, maybe we can just turn the lights on.
Like,
Wait till everybody's in.
that's much better, actually. Yeah. That was okay. Yeah, that's about where we were before.
Because it's too dark, it's hard to see the speaker, right? That's what I was thinking.
Yeah.
I have a flashlight.
Yeah.
Get all our iPhones out on flashlights. Huh. So what is cast go? What will it look like that?
Like, I haven't gotten it better.
Well, it was better than that one the other day.
Not really.
It was better on this.
Not like.
Oh, so this speaker will look okay.
Yeah, the speaker will be fine.
The comments. Maybe the contract.
Yes. Of course.
How are you?
Good, how are you?
Good, long time no see.
Yeah.
Been a while. We'll catch up after, I guess.
Yeah.
Well, good afternoon. My name is Matheus Grasselli. I'm the chair of the Math and Stats department here at McMaster, and it's an immense privilege for me to welcome you all here today at this event in honor of our friend and colleague Walter Craig. Much will be said throughout the day about Walter and his life and his contribution and his family and friends, so I'll be very brief in this introductory remarks. Walter passed passed away on January 18th, earlier this year, and there's hardly a day in the department that goes by without a reminder of this loss. From things like the graduate course that he was going to teach this term, to the ongoing supervision of many undergraduate students, graduate students, postdocs, his leadership and opinion on the searches for faculty members that we just conducted, to things like just having his door open at the 4th floor so that I could come there and have a chat in the middle of the morning and get a boost of intellectual energy throughout the day. So for us, the impact of this loss certainly is going to take a long time to absorb and comprehend. Throughout this couple of months, however, it's been a pleasure to work with our colleague, Deirdre Haskell, and with their beautiful daughter, Zoe Haskell-Craig, whom I met when she was this big, and now you can see for yourself, in organizing this event. As with anything in Walter's life, it was impossible to separate the academic from the personal aspects, so we decided to do a joint event that highlighted the entirety of his life and contributions. So the event will start with a talk now by Professor Jean Wayne from Boston University, who is a close collaborator and friend of Walter's. And Jean and Catherine Sulem are writing the obituary for the notices of the AMS. And I think Jean will present some of that now. Oops, it's the wrong time for it to disappear.
Oh. Good. Okay. So thank you very much for the introduction. It's really a great honor to be asked to speak at this celebration of Walter's life. Walter was a long time colleague, not colleague, but we collaborated for many, many years, and a really cherished friend. And Walter had many, many talents, but I think none greater than his talent for friendship, as the crowd here testifies to. So it's an honor to be here today, but it's also a rather daunting task. It's daunting, first of all, because the breadth of Walter's accomplishments and interests makes it impossible for me to touch on more than just a small fraction of his work today. But it's also daunting because as one of Walter's former postdocs emailed me shortly after Walter's death, he said, quote, "Walter was the best expositor of mathematics that I ever met," end quote. And somehow I have the feeling that whatever I might say about Walter's work, he's already said it better somehow, because he really did have just a gift for explaining mathematical ideas in ways that reached the listeners. But nonetheless, I would like to try this afternoon to tell you just a little bit, both about the influence that Walter's mathematics had on me and what I see as the influence on the mathematical community more generally. So Walter received his PhD in 1981 at the Courant Institute. He was a student of Louis Nierenberg. I'll say a couple words about his thesis later in this talk. He then went to Caltech for 3 years as a postdoc before moving to Stanford as assistant professor. From Stanford, he went to Brown, where he was associate professor and then professor and then department chair before moving here in 2000 to McMaster as the Canada Research Chair. And he remained here at McMaster for the remainder of his career, except for 2 years that he spent at the Fields Institute as director of the Fields Institute. And during that entire time, he carried on an extensive research program, which was influential both because of the quality of the research and influential also because of his service as a mentor to generations of graduate students and postdocs. So as I said, at even the most cursory glance at Walter's CV shows that I can't touch on more than just a fraction of his work. He published more than 100 research papers, several books, and his interests were very, very broad. And so just aside from the limitations of time, I'd be unable to do justice to all the subject matter in his papers. So for my discussion this afternoon, I'm going to try to take as a theme one of Walter's special interests, which was the study of water waves. So Walter first showed me this picture. It's one he loved very much. It's the great wave of Kanazawa. You may have seen it more recently because Walter chose it for the cover of his book on partial differential equations. So water waves was really a theme of Walter's research going back many, many years. But it wasn't actually where he started. I mean, so the first paper here on his list of publications is from his PhD thesis. His PhD thesis was on periodic solutions for forced dissipative hyperbolic systems. And then as I said, he moved to Caltech, where he began, he got interested in the theory of Schrodinger operators, and specifically their spectral properties. And so the next few papers are related to that interest. And then all of a sudden, sort of out of nowhere, there are these two highlighted papers which deal with what are called the Boussinesq and Courtevet-Gavry's limits for the water wave problem. And so it's with these papers that I want to start the discussion this afternoon, because they were the first published record of Walter's interest in waterways. And as I'll try to explain to you, they were really quite groundbreaking research, and research that's had an enormous subsequent impact on this area of mathematics. So I think everybody's seen a water wave. So you may have dropped a pebble in the pond, or a drop of water drops from the faucet into the bathtub, and you see the waves spread out. But those types of waves, they disperse very rapidly. So certainly in this picture of somebody dropping stones into the pond, those waves will have dispersed before they reach the other side of the pond. You'll never know there was a disturbance there at all. And that's typical of most of the waves we encounter in daily life. On the other hand, there are waves, for example tsunamis, which travel enormous distances, thousands and thousands of kilometers, without this sort of dispersive sort of loss of energy and structure that we see in sort of what you might call everyday waterways. And so why is there this difference that between these two different types of waves? And that's one of the things that we learn from Walter's initial work on water waves. So you might say, well, surely, I mean, we know we're mathematicians. Some of us are mathematicians. Not everybody's here a mathematician, but those of us who are mathematicians, we surely know what the equations that describe water waves are. So let's look at them. Well, even for those of us who are mathematicians, or maybe especially for those of us who are mathematicians, we do know the equations that describe water waves. We've known them for probably 200 years now, since the time of Euler. But they're really a quite complicated problem. So these equations will play a role, so I'm going to talk about them a little bit here in somewhat more detail. So here we're looking at a wave that's moving to the right, let's say, in this channel. So it's a channel of finite depth, which I've normalized here to be at depth 1. Inside the region, the state of the fluid is described by its velocity. So the velocity is a vector, so u1 will be the horizontal component of the velocity, u2 the vertical component. And we'd like to understand how the velocity of the fluid changes with time. And so these first two equations are, if you like, just Newton's law for the fluid. So the left-hand side of the equation describes the acceleration of the fluid, and the right-hand side describes the forces that act on the fluid. So there's a pressure force here in the first term, And then here in the vertical direction, we also have the force of gravity acting. So that's what these two equations are. So they're the dynamic equations, if you like. These next two equations are assumptions we make about the fluid or about the fluid's motion. The first one's the mathematical representation of the fact that water in everyday circumstances, and certainly in waves in the ocean, is essentially incompressible. So this is just writing out the fact that you can't really squeeze water very easily. The second one is a more limiting assumption. This is what's called the assumption of irrotationality, and it says there are no swirling in the fluid, so you don't have any vortices or things like that. That one's not always true, but it's often satisfied for the types of water waves that we'll be talking about today. And so that's actually, from a mathematical point of view, a quite important assumption because, again, for the mathematicians here in the audience, if you look at these two equations for just a moment, you see that by combining them, they tell us that each component of the fluid velocity is a harmonic function. And so we can bring to bear a lot of tools from harmonic analysis to analyze this problem. These three equations together are already pretty complicated. They're a nonlinear system of differential equations. But what makes this problem especially nasty from the point of view of mathematical analysis is that a part of the problem is to determine the domain on which we have to solve these equations, because we want to find the fluid velocity in the region omega of t that I've drawn here on this diagram. But that region will change in time. And so a part of the problem is to determine how does that surface of the fluid, gamma of t, change with time. And that's incorporated in these boundary conditions that I've written in the last line of the transparency. So eta is an additional independent variable that, dependent variable that represents the location of the free surface. So eta of x and t would be the height of the surface at position x at time t, and these three conditions are boundary conditions on the motion of the fluid. And so it's really that fact that we're dealing with what's called mathematically a free boundary problem that makes this such a difficult problem to analyze rigorously. So nonetheless, it's an important problem. I mean, we encounter waves all the time. And so even though people were frustrated in sort of attempts to rigorously analyze the full water wave equations that I wrote on the previous slide, they were so important that people began relatively early, certainly by the end of the 19th century, to try to derive approximations to these equations which were more amenable to mathematical analysis. And so the most famous approximations were by Boussinesq and Korteweg and de Vries, and in particular, they both arrived at this single, simple partial differential equation known as the Korteweg and de Vries equation, which was derived as a model to describe long waves of small amplitude. So you will have to quantify what we mean by long and small, but that's roughly the physical circumstances under which this equation was derived. And what Boussinesq and Korteweg and de Vries did was to make approximations to those complicated equations I showed on the previous slide, but which were reasonable approximations, but not mathematically controlled approximations in any sense. Nonetheless, in the 120 years since Korteweg and de Vries' work, people have used this equation extensively to model waves, and in particular, it's been used as a model of tsunamis. But it's a real question, I think, whether it is an accurate and appropriate model. And I want to distinguish between an accurate model, by which I mean do solutions of the Korteweg and de Vries equation accurately approximate the solutions of the very complicated system of equations I wrote on the previous slide. An appropriate model, by which I mean if you look at honest-to-goodness tsunamis, are these assumptions, which were made by Korteweg and de Vries in order to derive this equation, are they actually appropriate to the physical circumstance in question? And Walter was interested in both of those questions. That is to say, both accuracy and appropriateness. And so let me just go into a bit more detail about what we mean by small amplitude and long waves here. So imagine that this is a wave propagating to the right. So it's propagating in a channel or in an ocean, if you like, of depth h. The maximum amplitude of the wave will denote by A, and the length of the wave will denote by V. And then the conditions under which the Korteweg-and-de-Vries approximation is derived is that the ratio of the height of the wave to the depth of the channel is similar to the ratio of the square of the height divided by the wavelength. Okay, so note that A and H and B all have units of length, and so alpha and beta are both dimensionless parameters. And so this makes sense to talk about these ratios and compare these ratios, since we're comparing dimensionless quantities. And so those are the conditions under which this approximation was derived. And then you can ask, and Walter did, and so this is a slide that I actually lifted from one of Walter's talks. This was a talk he gave at a AAAS meeting in 2006, where he actually went and looked at the data from real tsunamis. And he asked, well, are these hypotheses that underlie the Korteweg-and-de-Vries equation really satisfied in this context? And what he found is that sometimes yes and sometimes no. And so that a kind of naive or thoughtless appeal to the Korteweg-and-de-Vries equation as an explanation of tsunamis may or may not be appropriate. And Walter was really concerned that, you know, there's sometimes a tendency, if you want to justify what you're doing, to say, oh, I'm working on problems about waterways, you know, things like tsunamis. And so, well, it's very easy to say that, but Walter wanted to make sure that when one said that, one was justified in saying that. So this is the first aspect of Walter's work on the Korteweg-and-de-Vries equation. He was concerned about whether or not that was actually an appropriate approximation for actual real-world geophysical situations. But that's not, in fact, the content of the two papers that I highlighted on his publication list. You can see this was 2006. Those papers dated from about 1985. And so those two papers were concerned with the question of whether or not the Korteweg-and-de-Vries equation is an accurate approximation to water waves. So there, what we're going to ask is, or what Walter asked is, suppose you take a solution of the Korteweg-and-de-Vries equation. As I said, that's a very well-behaved partial differential equation. We know a great deal about the solutions of that equation. Can we take the knowledge we have about the Korteweg-and-de-Vries equation and assert that that is transferable to solutions of the water wave equation? And for that, we have to know that the Korteweg-and-de-Vries equation is really an accurate approximation of the water wave problem. And so if you want to show that that model is accurate, you have to do basically two things. You first of all have to show that at any given time, the error you make in approximating the water wave problem by the Korteweg-and-de-Vries equation is small. So you want small errors at any given time. And then you have to check and make sure that those errors don't accumulate as time goes on. And it's really this second point that makes the problem so difficult in the water wave context. Because it turns out, and I'll explain this in a bit more detail in a few slides, that the Korteweg-and-de-Vries approximation makes interesting predictions only over very, very long time intervals. And so if you want to show that the errors don't build up over time, you need to compare the predictions of the model to the solutions of the true equation over these enormously long time intervals. And just to give you a sense of how rudimentary the mathematical theory of water waves was prior to Walter's work, it wasn't even known if the water wave equations had a solution over the KdV time interval. So there's a very first step in what Walter had to do. He had to show that even a solution existed, because that was just unknown prior to his work. And again, sort of a remark for the mathematicians here today. If you think about this, this is very similar to what you do in numerical analysis, where you talk about the difference between the consistency and convergence of a numerical scheme. The consistency would be analogous to showing that the error you make at any given time is small, whereas convergence, which is a much harder problem, typically corresponds to showing that the errors don't accumulate over time. Okay? Again, I can't somehow stress enough how little was known about water waves prior to Walter's work, and what a big impact his work had on subsequent research. And so I just went back and I looked in MathSciNet, and in MathSciNet I just said water waves. Show me all the reviews that say water waves somewhere, in title or subject or hash or whatever. And so if you look in the 70s and 80s, there were some comments about water waves. There were a few papers, 130 roughly a year on average. Many of them dealt with just the Korteweg-de Vries equation. Okay, they would say the Korteweg-de Vries equation is a model for water waves, and then they would talk about the Korteweg-de Vries equation. So it was kind of bumping along at 130 a year. And then here, this red column corresponds to the year in which the review of Walter's first paper about water waves appeared. And you see that after that, interest in water waves just took off. And it's continued to grow. I mean, it's a it's an enormous sort of field of mathematical research today. I mean, there was a special semester at the Fields Institute a few years ago. There was a special semester at ICERM 2 years ago. There have been workshops at the Newton Institute, workshops at Overwolfach. So now, if you are a young mathematician today, water waves seem like a normal part of mathematical analysis. But that was not always so. And while it would probably be overstating the case to say it was just Walter's paper that led to this enormous increase in the interest in water waves as a topic of mathematical research, it's, I think, undeniable that the influence of Walter's work on this problem did contribute to this growth in the study of water waves as a topic of mathematical analysis. And the other thing, Walter was a really outstanding advocate for mathematical ideas. So I think many of us here in the room will have fond memories of being at some mathematical conference and walking into the room, and there was Walter at the center of a circle of people talking about problems of common interest, problems that probably much of the circle hadn't realized was of common interest until Walter explained why what they were doing was related to waterways or related to something else. He just had a sort of infectious way of sort of bringing people into his circle, and an enormous generosity with his ideas. It wasn't, you would talk to Walter about a problem, it wasn't like, oh, I have an idea, let's write a paper. He would just give his ideas away because he thought it was important that people think about these things, that he realized that these were essential ideas and he wanted to convey them to other people. And so he worked enormously sort of informally, just talking to people, but he was also very active about organizing conferences and workshops. And so this was at a conference in Moscow on waterways that Walter helped organize in 2006. So again, I just cannot stress, especially for the younger people or perhaps the non-mathematicians here, how influential this work of Walter's was in terms of making waterways a real sort of compelling part of mathematical research. So now I'm going to go back and I'm going to tell you at least a little bit more in detail about some of the ideas that were underlying Walter's work on this approximation problem, because I think it really gives an idea of how deep Walter's mathematics were. Because again, as I say, this was just something out of the blue. It wasn't like Walter was just extending other people's ideas a little bit. This was just something new. I mean, it kind of didn't exist before Walter tackled it. So the first step in Walter's proof was he went back and he changed from what is called the Eulerian point of view to the Lagrangian point of view. So the equations for the water wave problem that I wrote down before are appropriate if you imagine yourself sitting in a laboratory and you have the wave in a wave tank in front of you, and you look at, in the laboratory there's a point xy, and you measure the fluid velocity at that point xy at time t. So that's what's known as the Eulerian point of view, and those are the equations that I wrote down previously. So Walter's first step was to change the problem into what's known as the Lagrangian point of view. And roughly speaking, that corresponds to imagining you, at time 0, you put a little tracer on each particle in the fluid, and then you follow where that tracer particle goes as time evolves. And so these variables capital X1 and capital X2 describe the location of that tracer particle, which is on the surface of the fluid. So it started at time 0 at point little x, and now it's moving along at time t to the location x1 and x2. And it turns out, and this is a consequence of the remark I made earlier, that inside the domain, the components of the fluid velocity are harmonic functions. Turns out that as a consequence of that fact, you can reduce the entire set of equations to this pair of partial differential equations that are just expressed in terms of variables on the free surface of the fluid. So that's already a good thing. I mean, we went from, I don't know, what did we have before? 4 or 6 equations to 2 equations, so that looks promising. But these are pretty nasty equations. If you're a PDE person in the audience, you'll recognize that these are not such nice equations. In particular, there's this mysterious quantity k of x here. K of x is the Dirichlet-Neumann operator. What it does is it relates the horizontal and vertical components of the velocity at the free surface, and it is again, its existence is again a consequence of this fact that the components of the velocity field are harmonic functions in the domain. And really, so this operator again became a kind of leitmotif of Walter's research. Again and again, he had a really, really deep knowledge of the properties of this operator, and he was able to exploit that so both from a theoretical side and then in collaboration with Catherine Sulim to develop very effective numerical methods for computing sort of water waves. And so his understanding of this very complicated operator turned out to be key to many of his mathematical accomplishments. So as I say, it's for our purposes some smooth function of the surface elevation x, and in particular can be expanded in a Taylor series. And so if you just look at the leading order term, which corresponds to expanding about the flat surface, so these would be very small waterways, it turns out it's just a Fourier multiplier operator whose Fourier symbol is hyperbolic tangent. So in particular, so Walter was very fond of quoting the saying that he attributed to Mark Katz, which was be wise and linearize. So let's follow Walter's advice and linearize the water wave equation. So here, these are these complicated equations that I have here. And all I've done is just throw out anything that's nonlinear. Okay? And if you do, you arrive at this system of equations, and you can, of course, differentiate the first equation with respect to time and reduce just to a single sort of wave-type equation for the surface elevation. Okay? And so if you solve this using Fourier transforms, then you find that you have a family of traveling waves x2 for the linearized equation with dispersion relation given by gk hyperbolic tangent of hk. So everything's great at the linear level. Okay? So, however, if you think about these equations, these waves, so the dispersion relation is sort of, the derivative of the dispersion relation is dependent on k, and as a consequence, what that means is that waves of different wavelength move at different speed, and this in turn means that localized solutions of the linear problem will just fall apart. Okay, so if you started with just a solution of the water wave problem corresponding to just a lump, like you might imagine a tsunami was, then it would not propagate across the Pacific Ocean. It would just, because different wavelengths that make up this lump propagate at different speeds, it would rapidly disperse. So if you want to account for things like tsunamis, you've got to include nonlinear effects. And that means that the whole theory becomes much, much harder. So what did Walter do next? Well, first of all, remember we said that the Korteweg and de Vries approximation corresponded to a very particular limit, one of small amplitude and long wavelength. And so he rescaled all the variables in the equation to represent, to incorporate that scaling. So he said, we'll take the amplitude of the solutions we're interested in to be epsilon. We'll take their wavelength to be 1 over square root of epsilon. And with that in mind, he defined new variables x prime, t prime, x1 prime, x2 prime. He took these new variables, he plugged them into our original nonlinear equations, expanded, at the moment just formally, so this is still just formal, and he got this equation. And so, again, for those of you who are maybe mathematicians or physicists or engineers, you may recognize that if I just set the terms of order epsilon squared on the right-hand side of this equation to 0, that's one of the forms of the Boussinesq equation. Okay, and it's, of course, again, for the mathematician, very, very ill-posed. And another troubling feature of this expansion is that the terms that I've just written of order epsilon squared on the right-hand side, while they are formally smaller than the terms on the left-hand side of the equation, they involve derivatives of higher and higher order of the unknown solution, which means that they're a very singular perturbation in mathematical terms of our leading order approximation. So, and we're not quite done yet, because remember, we were really aiming for the Korteweg and de Vries equation, so Walter went further. That involves a further rescaling, and again, let me make a comment for the mathematicians here. Suppose we set not just the terms of order epsilon squared to 0, but also the terms of order epsilon to 0. If we set the terms of order epsilon to 0, the only two terms that remain are these two, and that you'll recognize as just the linear wave equation. And so, to lowest order, we expect the solutions of this equation just to propagate either to the left or to the right with speed 1 in the scaling we've chosen. So we'd expect that the solutions to lowest order would depend either on x prime minus t prime or x prime plus t prime. So we'll look with that in mind just for solutions which to leading order depend on x prime minus t prime, and then they may depend on some additional slow time scale, which I'll call t double prime, which will be epsilon times t prime. And so Walter made that further scaling, plugged those new variables into the equation again, expanded again, and finally we arrive at this equation here at the bottom of the slide, which, if you stare at it for a moment, and if you make the substitution, call the derivative of x1 with respect to xu, then you see that this finally is, to the extent that we can ignore the higher order terms on the right-hand side of the equation, just the Korteweg and de Vries equation. So finally, from this procedure, we've at least reached the Korteweg and de Vries equation. But we've reached it by a series of reasonable approximations, but approximations that are quite difficult to control mathematically. And so here's just a few remarks about why the problem is difficult to control, even though we've now succeeded in deriving the Korteweg de Vries equation in a kind of rational way from the water wave problem, why it's difficult to control these expansions. And I should say that Walter's paper is more than 200 pages long. So this is really just not even an outline, I mean, you know. So, but these are some of the hard problems that Walter had to overcome in this paper. So first of all, as I said, it's the long time scale. I dropped the primes just for clarity, but this time derivative is with respect to this time variable t double prime. So t double prime is epsilon t prime. T prime was epsilon to the 1/2 times t. So t double prime is epsilon to the 3/2 times t. So if we want to solve the Korteweg de Vries equation on some time interval 0 to capital T naught, that corresponds to a solution of the water wave problem on this enormously long time scale from 0 to T naught over epsilon to the 3/2. And if you look back to the slide where Walter had worked out the values of epsilon for actual tsunami data, epsilon might be of order, I don't know, 1,000 or something like that. So this is an enormously long time scale. So we have to track the water waves for an enormously long time. The next difficulty is that these terms that we were ignoring, the higher order terms in epsilon, all involve many, many derivatives of the solution. And so we need to solve this problem in spaces of high regularity. And that, in turn, from a partial differential equation point of view, is quite hard because if you look at the linear problem, there's a kind of natural energy function for the problem. It's written right here. And what you see is that in PDE terms, this energy controls half a derivative of the solution, okay? And you want to solve the problem in spaces of high regularity. It's even worse because this controls half a derivative of the solution. If you look at the water wave equations, there's a full derivative in the nonlinearity, so it's not even clear you can solve the problem at all with this energy functional. But there is a lovely cancellation that occurs, and one's able to construct a theory for the problem based on this energy functional. But as I say, it requires an enormous amount of very subtle technical analysis. But Walter was able to push through that and prove really the first sort of rigorous approximation theorem for the water wave problem over the full timescales of interest in the Korteweg-de-Vries context, and show that really solutions of the Korteweg-de-Vries equation did provide accurate approximations to the solutions of water wave problems over physically relevant timescales. And so not only was this the first long-time approximation result for the Korteweg-de-Vries equation, but these types of approximation equations, like the Korteweg-de-Vries equation, come up in many other contexts. The nonlinear Schrödinger equation is a model for pulse propagation in optical fibers. The Ginzburg-Landau equation is a model for the evolution of certain localized structures in fluid mechanics. And since Walter's work, all of these sort of modulation equations have been shown to be accurate approximations in appropriate physical context. But Walter was really there first. And I mean, and it was such groundbreaking research that it's, I think, hard to overestimate its impact. So I want to now turn to a second theme in Walter's research. And again, this is a theme that spanned his career. And this is what are known as the small denominators. And again, these are linked to water waves because while, as I said, we can't really solve the water wave equations in general and have to resort to sort of Korteweg-de-Vries approximations and other types of approximations, there are certain special types of solutions of the water wave problem that we can analyze. And a couple of those, both of which Walter made important contributions to the understanding of, are traveling waves. So these are waves that travel with a constant speed and unchanged form. And then another type of wave are what are called standing waves. And so these are waves that stay in the same place. They stand there, but they oscillate periodically in time. Okay, and so in both of these cases, Walter made essential contributions to our understanding, and it turns out both of these types of waves are very important in the context of water waves. So, so this is where Walter and I first started working together, and so I took this picture. We were all, so that Deirdre, of course, and Walter, and Sergei Kuksin, who was also interested in these kind of small divisor problems. We were all on our way to a meeting at Oberwolfach. And so, I mean, I have the fondest memories of working with Walter. He was a wonderful collaborator. I mean, again, for the mathematicians in the audience, I mean, mathematics research can be pretty distressing at times. I mean, as another of my collaborators often said, "Yeah, alles wieder falsch. Everything's wrong again." Yeah, so, but Walter had an invariably sort of positive attitude, just a cheerful outlook. I mean, you know, no matter how convinced I was we were never going to finish this problem. Walter just always was sure we'd make it, and always was sure that it was important, and always came with a good idea at the crucial time. And so this is, I don't know, I like that picture a lot because it represents good memories for me. So what we're going to do here is we're going to try to. So now we have some general idea, thanks to Walter, about the existence theory for general solutions of the water wave problem. We can start to ask about more special types of solutions. And we're going to look at sort of periodic solutions. And there's a wonderful quote from Poincaré about why looking at periodic solutions is a good idea. So you know, you might think at first they're just of no practical interest at all, but they provide this precious, they're so precious because they have to only reach into this region which we might have thought unapproachable. So anyhow, I like this quote. First of all, I think it's a wonderful quote about, you know, why one might want to study these periodic solutions, but also because Walter really loved France and French, and so I think I had to have a French quote in this talk somewhere. So Walter wrote a very beautiful book about small divisor problems in French, so I commend it to you. So let's talk just a little bit about periodic solutions. So we all know about periodic solutions. So if you think about a pendulum bob oscillating back and forth, then if x of t is the position of the pendulum, it satisfies this famous, at least approximately, this famous differential equation, and the solutions of that differential equation are just a sum of sines and cosines, and hence all the solutions are periodic functions of time. So that's a single pendulum. Well, and that's an ordinary differential equation. So we're talking today about partial differential equations mostly. So the next equation you might think about, and if you haven't seen this, you can look it up in Walter's book on partial differential equations. So it's this little wave equation. So again, it's possible to solve this equation explicitly because it's a linear equation, and you find that every solution can be written as a sum of periodic solutions with frequencies that are some multiple of the fundamental frequency omega, where omega is related to the speed c and the length of the interval. And so what's the problem here? We just found a lot of periodic solutions. So why can't we do this in the water wave problem? And the problem in a word is, again, this nonlinearity in the equation, because the nonlinearity tends to mix periodic solutions together. And so what's the problem with mixing periodic solutions together? Well, the effects of mixing periodic solutions can either be kind of benign or quite drastically destructive. So the first person really to kind of systematically study this was Huygens. So Huygens was interested in clocks, and he discovered experimentally that if he took two clocks and if he hung them on the same wall, then those clocks would have, initially they'd have slightly different periods. I mean, you know, it's very hard to make an accurate clock. This was back in the 17th century. So I looked up what was going on in Canada, since I was going to talk here. What was going on in Canada when Huygens was working with his clocks. So it was working on about the time Montreal was settled, so a long time ago. So it's hard to make clocks that were absolutely accurate. And so you have these clocks, they keep slightly different time. But he hung them on the same wall, and he found that there was just enough interaction between the clocks as time went by that they would start to synchronize. And so the pendulum bobs would swing in synchrony after some time. So one effect of the sort of mixing and interaction of periodic motions is that it can change slightly the frequency. So the frequencies of these two clocks would change a bit so that they both synchronize. So you can change the frequency slightly and synchronize the frequency. The other, much more dramatic effect is the famous collapse of the Tacoma Narrow Bridge, and that's the effect of periodic frequencies, or nearly commensurate periodic frequencies, reinforcing each other and leading to a feedback phenomenon, which ultimately, in this case, led to the bridge collapsing. So if you have nonlinearity, which allows different frequencies in the problem to interact and mix, then you can get quite new effects that just aren't present in the linear equation. And so Walter and I started looking for periodic solutions of this nonlinear wave equation. And so if epsilon is 0, so we put in a parameter so that we could control the strength of the nonlinearity. So if epsilon is 0, you just get, again, solutions that you can more or less write down. They're all either periodic or generalization of periodic, known as quasi-periodic. And so again, for the linear case, we kind of know everything there is to know about this problem. And then when epsilon becomes non-zero, this nonlinear term, as I said, will allow these different periodic solutions to mix and interact. And the resonances which correspond either to the pendula synchronizing or to the feedback that led to the collapse in the Komenauer bridge, they'll occur if some multiple of the frequency of one of these periodic solutions is equal to some possibly different multiple of another frequency. So these are known as resonances, and they're really what can lead to the breakdown of the periodic motion. And so now we get to a kind of fundamental difference between the finite dimensional problem represented by sort of ordinary differential equations and the infinite dimensional problems that are present in these partial differential equations. So already, almost exactly 100 years ago, Lyapunov showed that for a system of ordinary differential equations, if you have a problem in which the linear frequencies are non-resonant, if none of these quantities k1 omega n1 equals k2 omega n2, if you have a non-resonant linear system, then for small nonlinear perturbations, those periodic solutions persist. Okay, so there's no problem really with continuing these solutions in the finite dimensional case. But unfortunately, that's no longer true for infinite dimensional cases like these nonlinear wave equations. And so even if for the linear problem there are no resonances, these quantities may become arbitrarily small because you have infinitely many of these quantities. So they may become arbitrarily small, and as we've seen, when you add nonlinearity, it can slightly change the frequencies of the linear problem. And so even if when epsilon is 0, there are no resonances, that may not be true any longer when epsilon is non-zero. And so there had been prior work to Walter's and my work, but using different methods, trying to understand periodic solutions for these nonlinear wave equations. But what Walter and I did was just to take a kind of direct attack on the problem. And so we said, well, if there is a periodic solution, then we should be able to write it as a Fourier series. And so we just said, okay, what conditions will the Fourier coefficients in this putative solution have to satisfy if such a solution is to exist? And so if you take this hypothesized form for the solution and plug it back into the equation, what you get is a sort of infinite set of algebraic equations for the Fourier coefficient. So that's what I've written there on that top displayed equation. And so you have these linear terms, omega j squared. The omega j's are just the frequencies of the linear problem, and then capital omega is the frequency of our hypothesized periodic motion. So you get those linear terms, and then there's some nonlinear term epsilon v hat, which we don't know very much about at the moment. And so the question is, can we find some Fourier coefficients u hat to satisfy that equation? So I don't know. That maybe doesn't look like progress. We started with one equation, and now we have infinitely many equations. So I don't know if that's a good thing. But there are ideas, or there are methods for solving complicated equations. One of the most famous and oldest such method is Newton's method, where you imagine you want to solve some equation. So I've just rewritten equation 22. So a solution of equation 22 would correspond to a point where this function capital F is 0. So we're going to look for a root of that equation. And so we take, according to Newton, we take an approximate solution. and we linearize the problem about that approximate solution and solve that resulting linear equation. And so you get a corrector to your approximate solution that's given by this formula right here, and that's of course wrong. So this d hat should be f of u 0 hat. Sorry about that. But in any event, f of u 0 hat is not hard to deal with. That's just the amount by which our approximate solution fails to be a true solution. That we know quite a lot about. The real problem is understanding how to invert this linearized operator. And so, so that's where sort of a nice coincidence in both Walter's and my background stood us in good stead. So what Walter and I noticed is that, well, if you look at this linearized operator, I haven't written it out for you, but if you do write down the formulas for it, it consists of a diagonal piece, which is pretty easy to understand, and then there's a complicated piece that comes from linearizing the nonlinear term. So how do we understand that? Well, what Walter and I noticed was that in the case where there was a term m of x in our original equation, so I won't flip back and show you the equation just for want of time, but if you set that term to 0, then you know the eigenfunctions exactly, and you can compute quite explicitly the linearization of the nonlinear term in that case. And it turns out that that term is small and is very local. So it's an infinite dimensional matrix, but it's an infinite dimensional matrix, most of whose matrix elements are 0. In particular, all matrix elements that are further than a distance 1 from the diagonal vanish. And so what is that? I mean, well, there's another very well-known linear operator with that same property, and that's the discrete approximation to the Laplace operator. If you look at the finite difference approximation to the Laplace operator, it has exactly these two properties that I had described here at the bottom of this slide. And so this linearized operator, which comes up in Newton's method, is very similar to this, where we have some small multiple of the Laplace operator plus a diagonal piece. And that's just a Hamiltonian operator of quantum mechanics. And as I say, by coincidence, both Walter and I had been interested in the spectral properties of such operators in other contexts. And so we were able to use the techniques that were originally developed in the quantum mechanical context to control the behavior of the inverse of the linearization that arises in Newton's method. And I said a little bit more here, but in the interest of time, I'll skip over these details and just remark that with these ideas, Walter and I were able to prove that, that these nonlinear wave equations of the type I showed on the previous transparency did indeed have lots of periodic solutions. You could describe a sort of curve in the parameter space such that for a Cantor set of positive measure of those parameter values, you actually do have a periodic solution. And so this is a picture of Walter lecturing about small denominators at MSRI in Berkeley in 1993. And it turned out, again, this was an example of Walter's persuasiveness. So one person in the audience was Jean Bourgain, and so Walter sort of convinced Bourgain that this was an interesting problem, and so Bourgain then extended these results to show that you could use these ideas to construct quasi-periodic solutions and periodic solutions in higher dimensional domains. And so again, it was a case where Walter was able to convey his enthusiasm for the problem to a much broader audience. And so Walter actually then, in some sense, this work was really concerned with understanding the effects of resonances on solutions of partial differential equations. And Walter's interest in this continued up to very, very recently. In particular, he began to ask analogous questions. We studied the wave equation on a finite dimension or a finite interval of the real line. Walter asked, what happens if you ask analogous questions for partial differential equations defined on all of space? And it turns out that there's a very interesting difference in the theory in this case. Instead of considering sums where the denominator of the sum are these combinations of frequencies of the linear problem that we talked about in the context of small divisors, one now gets integrals. And so you're dealing with singular integral operators. And so recently, Walter has some very nice results. For instance, a paper with Katrin Sulim about these kinds of transformations specifically in the context of waterways, how you can apply these types of, they're called normal form transformations, and then also with Salvatella and Wong for the nonlinear Schrodinger equation. So again, sort of transferring ideas from finite dimensional dynamical systems theory to this infinite dimensional context of partial differential equations. And so now I'm running short of time, so I'll just say a very, very few words about, as I said, by a happy coincidence, both Walter and I had been interested in questions of Schrodinger operators before we started working together. And Walter's interest in that goes all the way back to his time as a postdoc at Caltech. He studied the sort of spectral properties of these kinds of time-independent Schrodinger operators, and in particular, whether the eigenfunctions of this operator were extended or localized, which has consequences for the transport properties of the resulting problem. And so that interest of Walter's has continued again throughout his career. And very recently, there's a paper with Robert Brandenberger, which extends some of Walter's past work, in which he gave a new proof of Anderson localization, which is a phenomenon in which sort of randomness in the system can cause the eigenfunctions to localize and hence inhibit, say, electrical transport or some transport phenomena in these types of equations. So again, there's a few words about proof there, but I think in the interest of time, I will skip those. There's another very beautiful paper where Walter, maybe I'll say just a couple words about this a minute. So this was actually quite early in Walter's career, his time at Caltech. He began to look at Schrodinger operators in which the potential, so here these are discrete Schrodinger operators from the lattice, and so the potential function B, Walter chose it to be an almost periodic function. And so one might expect that the case in which the potential is almost periodic would behave similarly. It would be almost like the spectrum of a periodic potential. So, but it's not, okay? What Walter found was that it's completely different, or at least there are examples of, I'm sorry, this should be almost periodic, not quasi-periodic, but there exist almost periodic potentials for which this Hamiltonian operator has a complete set of exponentially localized eigenfunctions. And so that's typical of the case where the potential is a random function. And so one finds somehow that the almost periodic case is actually closer to the random case than to the periodic case, which is, I think, a very surprising result. And again, I said a few words about the proof, which I will skip over. And just, well, what should I say? I mean, there's no time to tell you about Walter's work on numerical methods for water wave equations, smoothing dispersive equations, properties of traveling waterways. But maybe I'll just say one thing, just to give you a sense of how broad Walter's impact was. If you look at Walter's four most cited papers, I've only had time to discuss two of them this afternoon. So there are two more whole fields of research to which Walter contributed in an essential way that I haven't even touched on here. So I'll stop there, but you know, this another picture of Walter that I really love because, as I say, his sort of unfailing good cheer sort of helped me so often in my research, and I'm sure many other people here too. So thank you.
This was a mathematical talk, and I had never been to a mathematical talk with Walter. See, we missed him.
Just to ask, I wasn't sure what you meant by aerial pumps for those equations.
Yes, so sorry, that's a technical term that crept in there. So it means that you can start with initial conditions for the equation, which are very close, and after a short time, the solutions are very far apart. So in other contexts, it might be called sensitive dependence on initial conditions or something like that. So
I have a question. In the beginning, you said I do some water waves disperse and others not. And when I was taking water waves classes with Walter back in the late 80s, early 90s, he described this as a difference in dimension, that regular water waves expand out in 2 dimensions, they disperse as energy remains constant. But one-dimensional water waves stay the same. So are you saying that there's something else going on in addition to that?
No, that's a very good remark. So the idea is that what we looked at here, what Walter studied in this paper, was a sort of one-dimensional model for water waves. However, that turns out to be appropriate in certain physical circumstances, because you often see waves in deep water which are essentially constant in one direction and changing only in the transverse direction. So in that situation, you can model the physics by a one-dimensional water wave problem. But you're absolutely right. The dispersive properties of the wave are very different depending on the dimension. And in fact, one of the things that I didn't talk about here was Boulder showed that under certain circumstances you cannot have localized traveling water waves in 3 dimensions, for instance, basically because of the dispersive properties. Yeah. Yes.
So I have a somewhat non-mathematical question.
Okay.
So you referenced many times Walter's optimism while collaborating. Can you share a vignette or a story where you were blocked somehow, you felt pessimistic, but somehow Walter allowed you as a collaboration team to navigate around something? I think that kind of a story could really help bring to life this thing that you're emphasizing about.
Yeah, I mean, sort of just, I guess it was just a general, I mean, I don't have a specific occasion in mind, but just, Walter always brought such optimism to our work together, and so I can't put my finger on a specific instance. Maybe if I thought a bit longer, I could, but just a general sense of we can do this.
And that's perfectly fine, because the second part of this event, which we're going to migrate to now, will be at the faculty club. So just follow people who are from here. It's very easy to get there. And what we're going to do there is exactly have an opportunity for first some people who had prepared remarks to share stories and vignettes and insights about Walter's contributions in life, and then we'll have an open mic portion where, if you remember that